The interplay between semi-Dirac fermions, altermagnetism, and Magnons introduces a profound framework for understanding emergent phenomena in spintronics, energy dynamics, and attention processes. By integrating these principles into the concept of self-sustaining feedback loops, we explore how systems, whether quantum, material, or cognitive, can propagate and refine their states while maintaining stability and adaptability. Directional dynamics and paying forward attention. Semi-Dirac fermions. These quasiparticles, which exhibit massless behavior in one direction and massive behavior in another, introduce an inherent directionality into their dynamics. This directional mass acquisition mirrors the concept of paying forward attention, where effort and energy propagate along a defined path, influencing and shaping outcomes downstream. Altermagnetism. The alternating spin polarization in altermagnets reinforces the directional nature of energy flow. This alternating structure acts as a feedback mechanism, guiding the propagation of spin waves and stabilizing magnetic textures through inherent symmetry-breaking properties. Magnons, the quanta of spin waves, serve as carriers of information and energy within this framework. Their behavior in altermagnetic systems, especially when coupled with semi-Dirac fermions, represents the propagation of dynamic attention within a feedback loop, where intention, or external energy inputs, initiates Magnon movement. Tension, which includes interactions like DMI or spin-orbit coupling, challenges and refines their path. The output informs and evolves the spin system, creating new configurations. Self-sustaining feedback loops. The self-sustaining feedback loop within this system operates across quantum and material scales, integrating initiation. Semi-Dirac fermions guide the initial dynamics with directional constraints, analogous to how attention is directed toward meaningful inputs in cognitive processes. Their anisotropic mass behavior sets up a framework for focused propagation. Propagation. Magnons, influenced by the alternating spin polarization of altermagnets, propagate through the system, carrying information and energy in spintronic circuits. This propagation reflects the concept of paying forward attention, where energy invested upstream influences outcomes downstream, refinement and stability. The antisymmetric exchange interaction, such as the Dzieloshensky-Moria interaction, DMI, refines these dynamics by introducing chiral spin couplings that stabilize spin textures like skyrmions or helices. This interaction arises from spin-orbit coupling in systems lacking inversion symmetry, making it essential for both refining the energy flow and stabilizing emergent phenomena. In cognitive terms, this mirrors how tension challenges and reshapes attention to ensure adaptability and clarity. Emergent output. The outputs, such as topologically protected spin textures or robust Magnon currents, feed back into the system, evolving its structure and refining future dynamics. This mirrors how attention, when paid forward, fosters conditions for clarity and connection. Emergent phenomena in the feedback loop. Magnonic currents and energy dynamics. Magnons in altermagnetic systems, coupled with semi-Dirac fermions, exhibit anisotropic transport properties. This directional behavior reflects the propagation of energy in a feedback loop, ensuring that inputs lead to meaningful and stable outputs. By stabilizing magnonic currents, the system achieves efficiency in information transfer, analogous to the flow of focus in cognitive feedback loops. Topological protection. The interplay between semi-Dirac fermions, altermagnetism, and antisymmetric exchange interactions like DMI creates topologically robust states. These states ensure that feedback remains stable even under external perturbations, akin to maintaining clarity and adaptability in challenging cognitive scenarios. Dynamic adaptation. The system's ability to adapt its spin configurations based on external inputs and internal interactions highlights its self-sustaining nature. This dynamic adaptation parallels the refinement of attention, where inputs reshape perception and perception refines future attention. Applications and broader implications. Spintronic devices. Devices leveraging semi-Dirac fermions and altermagnets could propagate magnons with unprecedented efficiency, using feedback loops to stabilize and refine spin-based information processing. Cognitive analogies. The self-sustaining feedback loop in these systems offers a metaphor for cognitive processes, where attention, intention, and tension interact to refine focus and generate clarity. Quantum to macroscopic systems. This framework bridges quantum scale dynamics, Semi-Dirac Fermions and Magnons, with macroscopic phenomena, robust spin textures, demonstrating how self-sustaining feedback loops operate across scales. Conclusion. By integrating Semi-Dirac Fermions, Altermagnetism, and Magnons into the concept of self-sustaining feedback loops, we uncover a unified framework where directional dynamics, emergent phenomena, and topological protection converge. The inclusion of antisymmetric exchange interactions, such as the Dzialushinsky-Moria interaction, clarifies their role in stabilizing energy dynamics and emergent spin configurations. This model not only advances spintronics, but also offers profound insights into energy propagation, cognitive attention, and dynamic stability across systems. Whether in quantum materials or human focus, the principles of paying forward energy and maintaining balance through feedback loops form a cornerstone of emergent complexity.